Hello, everyone. Hello, Jonas. Hello, Marcos.
Hi, everyone. Hi, Julia, Marcos.
How are you guys
Hello.
doing? So today we have a really interesting webinar, guys, right? Because I think that this webinar was inspired by the request that we have received from our customers and our users, like what is hiding behind these calculations, behind our models. And I think that everyone here is really curious to learn. But from my side, Marcos, I'm really curious on something. What common mistakes do you see engineers do when it comes to planners design, comparing to conventional?
Well, one of the most common mistakes, I think so, or common mistake that I can find is that when you are doing the electrical design of the planar, that you are doing a lot of layers, and then you realize that you cannot do it or manufacture the PCB. That could be a problem because at the end the PCB are limited in the terms of layers and also the copper, and then you can create a perfect design, and then you can see that it's not feasible regarding the manufacturing point of view.
So that is what you commonly see being made as a mistake. Is it something also for the experienced ones, or like when you first start doing planners?
Well, at the beginning, maybe you start and then create the winding as you want, and then when you move into another tool like Altium, something like that, okay, to create the layout, you realize that there is no way to do that, okay, or maybe when you are ordered the PCB.
Okay, I see. And Jonas, I know that today we're gonna say a lot about it, but I'm also curious, like, why is planar loss modeling way trickier?
Compared to conventional magnetic component, what is tricky is the ratio. Like the PCB traces are extremely thin and wide, and that can induce a lot of eddy currents. I will explain a lot about this later in the talk.
Okay. I don't wanna steal more of this magic, but before we start, I know that today we're gonna see a lot of our tools, so I'm sure that we may have some newcomers here. So I would like to briefly explain what the audience is gonna see regarding our tools to have a better idea. So please let me share really quick. So firstly, we have our Frenetic AI, which is basically our agent for power converter and magnetic suggestion. Also here, you have the automatic LT-SPICE and file generation. But the limitation that we have here is that you cannot edit. So once you have your magnetic specs suggested, here is when our magnetic simulator comes, which is basically all the magic happens here. So you can validate and customize your magnetic part. You can design and simulate your transformer, your inductor, play around with cores, windings. Basically, you have control all over the parameters and play around. And like you can have a magnetic part in a few minutes. And last but not least, we have our newcomer, the Planner tool, which offers full simulation capabilities, parasitics, losses, effect of the gap. So here you have like all the platform and what is included inside our Frenetic architecture. I think that, guys, the stage is all yours, and we can go deeper to what's behind our models today.
Okay, so basically we have two parts today. One is a more theoretical part, explaining a little bit the models we are using and why we are going this path. We go the path we have chosen, and the other thing is then from Marcos. He will make a demonstration of the tool and also how the models that I was just explaining, how they actually work in practice. So the topic is the science behind our planar magnetics models. And I would like to go to the next slide, but it's not changing. 1 second. Okay, so there is a slide I have shown already before, so some of you might have seen this, but if you have solid round wires, so I'm starting now with a current approach to loss calculation, so what we are usually using in Frenetic simulator, and then I will explain the limitations, so what is actually the limitations and why does it not work for planners? And then our solution that we have chosen for planar magnetics. So what you can see here is basically just a core with a lot of windings around it and air gaps. So if you want to calculate the losses in one of these terms here, you need to know the current distribution, and also the magnetic field inside the winding window. So how are we calculating this? We are doing this by having two approaches. I go a bit quickly through this. If you have questions, I'm happy to provide additional literature about this, because this I already explained a few weeks ago. But basically, in order to calculate the magnetic field, we need to account, for instance, for the magnetic field due to the fringing field of the air gap. So what we do is, this is the magnetic core here, and they have a gap here in between. And what we do is we replace the gap through a fictitious current, which leads to a magnetic field around it that has the same value as the air gap had before. And what we basically have to do is the value of this current is equal to the magnetic force of that drops across the air gap. So basically, if you have the current that we chose is the magnetic flux times the reluctance of the air gap. So if you increase the magnetic flux, you directly proportionally also increase the magnetic current. So far so good. This is the first step. The next step is that we use a method of images or mirroring method. We get rid of the magnetic material, so we have a magnetic conductor that is in vicinity of a magnetic core, and you can show that the magnetic field actually is exactly the same as if there would be no material, but instead of the material you have another current that is the mirrored one of the original one. So the magnetic field up here did not change by removing the material. So why I'm all doing this, I think becomes clear in a second. You have the winding window, and you have now the conductors plus the conductors through to the air gap. Now you do this mirroring, which is a kind of an infinite amount of mirroring. We stop after some iteration, but what you end up with is a big plane with lots of conductors. And we are interested in the center window. That's where the actual window is, the magnetic field. So what is the magnetic field in this conductor, for instance? It's a superposition of the magnetic field due to every other conductor. So I went quite quick, but the idea is get rid of gaps, get rid of material, and having only a plane of lots of conductors. And when you have that, well, what you actually have is then the magnetic field through an inductor. And that allows you to calculate the proximity losses. And proximity losses is super critical for what I'm going to explain later. Now, forget about in the slides, there are a lot of equations. The only thing I want to show you here is if we know the current, which you usually know through a conductor, and the magnetic field through a conductor, then you also know the losses due to skin and proximity effect. This is the equation for the proximity effect. Now, so far so good. Now, but in planners, that's what I said before, we don't have a round conductor as here. What we have is a conductor that looks more like this. So it's first of all, it's rectangular, but also the ratio H to B is very big, because you usually have a very thin height and a very big width. The width A is very big. Now, if you have a conductor and through such a conductor, which is a special case, the magnetic field, as soon as it has a component which is orthogonal to the surface here, the losses can increase a lot. But not only the losses increase a lot, what actually increases a lot are the eddy currents, way more than in the solid round conductors. And these strong eddy currents significantly distort the magnetic field. And this you cannot neglect in planar. So you see here that if the magnetic field has an orthogonal component to the plane or to the PCB traces, it induces so high eddy current that it kind of distorts the field, something we did not have here. And because we didn't have it here, we also have it here, but it can be neglected in most of the cases. But here you cannot neglect it anymore. So our approach that we went or chose in the past is not working here. Yeah. And now we decided how to move forward, right? So we have a much more complex methodology how to calculate the magnetic field, but we need to calculate the magnetic field in order to account for proximity losses. So what we did is we built this planar app, and if you look what models are running behind the planar app, we have the loss model that I was explaining before, which is super difficult, and we used an approach called finite element method. So basically the whole space is cut into small pieces, and then the magnetic field is calculated by solving Maxwell equations. We also have in the planar app the capacitance model. This is something which is important for planners because capacitances are generally a bit bigger than in normal inductor or transformer. Something we have to account for, but it's also something we want to release in Frenetic Simulator. And the third thing we have is the leakage inductance model, which at this stage we use the analytical model that we already use in Frenetic Simulator. And if you're interested in learning more about this, I think the easiest is to contact us and we can send you our model fact sheet. Okay, so far so good. So this is the first time in Frenetic that we use a FEM approach. And why are we using this? Basically, the finite element approach is ideal because it can handle any geometry and it solves the problem numerically. And particularly, we use the tool COMSOL. The FEM directly solves Maxwell equation. And so with this, all relevant physical effects are included, such as skin, proximity losses, parallel windings, and so forth. Now you can maybe ask yourself, why didn't we do this in the past? Well, there is a disadvantage to using FEM, and it's a speed. It takes longer, and you will see this in the demo, to do a calculation. It takes up to 20, 30, 40 seconds. So you have to be a bit more patient with this approach, which has some disadvantages, especially if you want to do a lot of designs. But that's something, this trade-off we had to take in order to accurately model planners. Now we have capacitances, and concretely we use the primary open circuit capacitance, which allows you to determine the first resonance frequency, which is usually a kind of limit, shows you the limit to up to which frequency you can operate a design. Then maybe I will explain a bit more in detail. We have as FEM approach, we use a 2D model. Just 2D is faster than 3D, so we use 2D. But at the same time, we have a quite advanced approach how to calculate from 2D to 3D. And it's so-called a quasi 3D modeling concept, which has been developed by Richard Schlesinger, which is actually also working for Frenetic, and he was actually implementing all the COMSOL model. In his dissertation, in his thesis, you find more information about this approach. But it's something I would like to explain a little bit in detail. So if you see here, this is an E core, and you see the windings, like say the PCB traces around the core, like here. This is an example. Let's take a picture taken from his PhD thesis. You can see that depending on which section we simulate the losses differently. So here we have a different model than here or here and so forth. But especially important for planar is how we are considering here the part, the roundish part, the corner part here. And I would like to show this on an example. Let's say you have high eddy current losses. This is a bit difficult to see, but this is the core. Then you have the PCB here, and then you have one trace here. Let's say the losses are high in the inner side of the core window. So this would be here. So let's say you have high losses here. Many people calculate with the mean turn length. So they just take the average length of this turn, but because it's a planar, which has a very high width, this is of course a huge approximation. The length I would account here, multiply by, I would then, the 2D, 3D approximation would be multiplying the losses by this length. But actually the losses occur only here in the center. So here, so they are seeing much lower distance. So we account for that. So the losses that occur here, we multiply with a longer length. The losses here, we multiply with a smaller length. And like this, we account for effects that it's very important where actually the losses occur. And especially for planners, this is critical. So I hope I explained, it became clear. If you have questions, ask me. Yeah. So how are we then moving on? I think this is pretty straightforward. We have the geometry. So the app that you will see actually provides create the geometry and input data, and then it goes into the console model where the losses are calculated by first creating a magnetic mesh. Then all the boundary condition, interconnections, and so forth are defined. Then the simulation happens, and then the post-processing and the losses are extracted and being sent back to the planar app. And the same, more or less, for capacitance. Okay, that was the theoretical part of this webinar. If you have questions, happy to answer later. I hope I explained the things clearly. I know not everything was easy to explain. Let's move to Marcos. He has a demo prepared for us.
Okay. Okay, thank you, Jonas, for the explanation. Let me share my screen, and I will show you. Okay, can you see my screen?
Yes, you can, or we can.
Okay, perfect. So, well, if you attended the last webinar last week, I also showed you a phase full bridge case with a planar one, but today I would like to bring you to see also the models and what Jonas are explaining, which is a flyback converter. And why flyback? Because at the end, it's very common right now to use planar transformers for flybacks, because you can allocate also multiple windings, and the restriction in the size are very critical right now, and also because they have a gap, okay, because the gap is necessary to store the energy to deliver the power for the primary to the secondary. So we can see how the gap affect also to the losses. So if we start with the first, let's say, tool that Julia explained it before, okay, which is our AI assistant, you can, let's say, create a flyback by scratch, okay, filling the input and output voltage and output power, and specify things like the switching frequency. So effectively, you will have the schematic, okay. In this case, it's a complete schematic with an IC controller and also all the parameters that you need to simulate the thing. And here there is an important thing, which is that we have a auxiliary winding, okay, that I will talk also later. So here, if we suggest a magnetic design, the thing that we see is a concentric solution, okay, which is fine in the way that, well, we can use this as the final solution, which in this case is an E2513.7. But in this case, the height, well, it's 7.5. It could be considered as planar, okay? But in case that you want to integrate, for example, the transformer inside your PCB, this is something that is typically done. You can create the winding in the PCB as well. So let's move forward to the magnetic simulator. Okay, this is our second tool. Okay, this is more when you want to edit the design. Okay, more for the conventional point of view. So changing the core, changing the windings, running different simulations. Also, you can check or you can change things like, for example, I want to work on CCM mode, so I can change the magnetizing inductance in order to work in CCM, okay? You can also add different operation points, and then what we can do is also to design the planar core, okay? So if we move to the core optimizer, we can compare different planar shapes. First of all, we need to, this is very similar to the area product method, more or less, okay? So, but it works with peak limit, okay? So we can put, for example, peak limit 250 to have some margin regarding the saturation. We can pick a family shape, in this case, the planar. We can work with a planar E, Okay, maybe it's better a planar ER because it has a round pole, but let's work with planar E, which is cheaper. And the material, we can choose something generic. We can pick, for example, the N95, okay? And if we plot the cores, we can check in each core, okay, and the number of turns. We can pick one of them and then apply. And here we can check the core, okay, itself. If we run the core, what we can have here is the variable space that we have for the winding, and also we can do some adjustment here, like for example, changing the number of turns, and we can also calculate the gap and run it again, okay? So then imagine that you want to use this core, which has a total, this is the total size of the core, and you want to allocate a conventional winding. You can move to the winding and suggest a wire, but there is a problem, which is that there is no winding fitted in core with a variable current density. What that is mean? That the wires that you want to put inside the core has a very high current density. So finally, that ends in a very high temperature, and there is a potential risk of a thermal runaway, okay? That means that you cannot do the design. No, you can do it. You can pick the wires and you can try different options, okay? But at least at the beginning, this shape is not suitable for allocate a winding inside then. So we can use the planar and create a planar or a PCB, okay, to allocate the winding, and also we can use this to integrate it in our PCB. So the first thing that we need to do is to remove the coil former. So we have the height and the width variable here, and then we can move to the planar design and simulation tool. So here we can pick the core directly from the list, okay? In case that you want to customize something, you can do it, okay? Modifying here the values, and we need to introduce the gap. So in this case, we have one gap, and the size of the gap, we can check it here, which is 0.18, okay? And the gap is placed here. If you have a gap also in the lateral leg, you can mirror it, or if you have multiple gaps, you can also increase the number of gaps here, okay? This is more for application with a very, very large gap. Then we can set the PCB winding, let's say. This is the space that we will have for allocate the turns inside the core, okay? So we can divide also this in 2, 3, 4 PCBs in case that we want to have a separate component, or we can limit it to our PCB thickness. For example, if your PCB thickness is 3.2, you can put here 3.2, okay? In this case, we can put 85% of the core height, something like this, or 86, and then we can move to the PCB, to the windings. So here, well, first thing, we have primary and secondary, but we have also an auxiliary winding. So you can add a winding here, which is placed here. Then we need to put the number of turns. So if we put here, which is, well, we can check it here, is 25, and the turn ratio, it's 5 and 5. Okay, so we can put here 25, 5 turns, and 5 turns. And then the last thing that we need to put here before designing the traces are the reference current. What is the reference current? Basically, it's the RMS current that you have in each winding. So you have here 0.44 for 4 amps more or less, and 0.1. So we can write it here, and these reference currents can be used to calculate in real time the current density. So you can check quickly if the current density is okay or not. So then when you have this fillet, the next part is to designing the winding. The first thing that I see here, well, we have a lot of layers. That's the first thing. And secondly, we have layers out of the core window. We can adjust the number of turns per layer. So we can put, for example, 5 layers. Sorry, 5 turns. So we have a total of 5 layers. Then we can modify things like the distance between the turns. For example, 0.3. And we can also do modify the distance to the PCB. In this case, I want to keep it in 0.5 because it's important also to take into account the isolation, okay? We can do the same for the secondary side, okay? So we can, for example, put 1 turn per layer, something like this. in decreasing at the distance between the layers. In this case, it's not necessary. We can keep it even if the current density is high. And in the winding 3, we can put it all the turns in one turn, in one layer. Modify the distance between the turns, something like this, okay? And then after that, what you can do is to doing the interleaving. But before doing the interleaving, let me show you the leakage model and how it works. So imagine that you have this configuration. Then you need to just upload the waveforms, the CSV file. You can extract it from here, from Frenetic Simulator. So you can click in here, download it, and upload it here, okay? So you have the waveforms for the winding 1, winding 2, and winding 3. And you can simulate up to 10 harmonics, okay? Here, the most important ones in flybacks, the DC component and the first harmonic, the fundamental frequency, but it's also important, for example, the third harmonic or the fifth, okay? Which are also components that has some amplitudes, okay? What is the compromise? The higher the number of harmonics, the higher the in simulation time, okay? So these 30-40 seconds that Jonas explained it before can be increased to 1 minute, 2 minutes, something like that, depending on their harmonics. So then we can run here the complete simulation, but first we can run the leakage, because at the end, as Jonas explained it, the leakage model are analytical models. So it's very quick to do a first simulation and check the leakage inductance in between the primary and the secondary, and between the primary and the auxiliary winding. So the first thing that I see here, the leakage inductance is very high. If we compare it with the conventional solution, we have here 1.6. And that's weird, because typically the planar transformer has less leakage than the conventional transformer. But this is because we don't create a interleaving or a proper interleaving here. We can do it like this, moving the PCB layers. So we can do something like this, okay, moving its layer. Or we can put this one on the top. Okay, and the only thing that we need to consider is the auxiliary winding. We can put it, for example, here, okay? And then if you're running again, you can see, okay, so in this case, we reduce the, sorry, because here I think that we can optimize a bit more. If we move it this, okay. So here we have like a perfect interleaving, okay? And you can check quickly how the leakage changes. And also in this case, the tertiary winding has more leakage. So then you can run the complete simulation, and we can see the losses and also the open circuit capacitance that we can calculate the self-resonant, the first resonant, using this value and the value from the primary inductance. So it's in this case is 350 microhenries. Well, just an off topic, okay, in the meantime, once this is running, here, one important thing, okay, that we can also use the leakage model to fix it, that is the leakage between the primary and the tertiary winding, okay, or the auxiliary winding. If we have the auxiliary winding on the primary side, it is very important to reduce this value, okay? Not only this one, which is also important for flybacks to avoid voltage spikes on the primary side, on the MOSFET. And this value is also important to improve the regulation, okay? And also the step response of the system, okay? So things that you can do is, in this case, as we have 9 microhenries, we cannot move this to another position and, let's say, improve the leakage too much, okay? Well, we can do it. We can move it, okay? That, for example, we can put it on the middle, okay? And then we can run in again the leakage inductance, and we can see, well, in this case, we can improve a bit more, okay? These are the results for the simulation. So as you can see here, we have DC losses, we have AC losses, and well, in the winding 3, it's practically 0, and we have the total losses, which in this case are fine. And we have also the capacitance. So, well, continue with the topic of the auxiliary winding. If something that you can do to fix this, okay, and to improve is to add parallel, okay? So you can, for example, add here one parallel more, even if it doesn't matter regarding the losses, but this can improve the coupling, okay? And you can put or place this in another position. So you can, for example, do something like this, okay? And improve the coupling, okay? And you can quickly check here if you're running the leakages, and you can see how only adding one layer, how we can improve the leakage inductance. Okay, so finally, to conclude the demo, as the simulation takes some time, well, you can compare different simulation if you export the design, okay? This is a new thing that we introduced respect to the last week. And you can also import the design. So I have here some designs. It's the same design. Well, this is the same design with the nominal gap and without any interleaving. So if you check the simulation, the losses, which in this case is 0.67 watts, which is not too much compared with the other, okay? If we increase the gap, we can see also the losses, okay? Moving to the simulator, in this case, it doesn't increase too much, okay? And if we remove the gap, okay, this one, okay, it's not a practical case because at the end you need the gap, but imagine that you don't have the gap. As you can see, the losses are reduced in this case drastically, as from 0.76 at 67 to 0.51, okay, which is quite important, okay, in terms of the overall performance of the system. And yeah, that's all from my side.
Perfect, Marcos and Jonas. Thank you very much for this insightful and interesting webinar. I think we've finally revealed what is being hidden so such a long time and everyone is asking. Before we jump to the Q&A, I just wanted to say to everyone, because I have been receiving a lot of requests for the documentation explaining our planar models, or how can someone get a deeper demo for our magnetics or design tool. I will write down my email here in the chat. So anyone who is interested to receive the documents or wants a deeper demo, please reach out to me. And I think we can jump to the Q&A. Okay, let's see.
I think there is one question only.
Yeah, I can see two questions.
Is there a possibility to implement two separate PCBs to realize the safety isolation with isolation tape instead of relying on the FR4 material? Now not, but this is something we just discussed last week. So this is something we have to consider, yes. So version, I don't know. It's something we heard now. I heard it many times, so we will try to implement this.
I think we have also another question before that from Nikolai.
Where is that?
In the Q&A, hello, the coupling from Frenetic platform to console. Can you see Jonas or Marcos?
The coupling from Frenetic platform to console is done automatically via cloud computation and is done only for 2D. Yes, you don't need a console model or something. It's all in the cloud and it's 2D FEM because we have this quasi 3D approach that gives us very good results. Is there a possibility to implement two that's the same question I already answered, but there might be one more. No, I think these are the questions.
Okay. I think we are done for today. We're done for this webinar. I want to thank you again, guys. You also have another one later, right? For the USA audience and also for anyone in the Europe who didn't manage to make it now. So thank you again for your time. I think, sorry, we may have another question. Okay. I think we can also reply to these last questions.
Is it also planned to implement mixed version of planar, winding and PCB? That's a good question. Probably yes, but not in the very short term. You mean to have solid round or Litz wires and a PCB in the same magnetic, if I got it right. So this is something we will consider at some point, but yeah, I cannot give you now a date when we will have that.
Okay, Jonas, thank you very much. Jonas, Marcos, have a great rest of the day. And everyone,
Thank
we
you.
will see you again next week. Okay?
Thank you, everyone.
Goodbye,
Bye-bye.
everyone.
Bye-bye.
Bye-bye.